Okay, so let's assume that we know the expected value of some random variable y. Okay, following the expected value, the definition that we use for expected value. And now we would like to show that through importance sampling we can use this expected value in order to compute the expected value from some other random variable x. Right, so yes, we can do that as long as all possible values of x do exist in y. That is, we have the coverage conditions that we discussed before. Okay, so in that case we can simply write the expected value of random variable x as a summation over all possible outcomes of y's or summation of the outcome, that outcome, multiplied by the probability of seeing that outcome under distribution, the distribution of x, right, the random variable of x. So now actually the proof is pretty simple. We multiply and divide by the probability of seeing that outcome under distribution y, under the other random variable. And now we can see that we have precisely the importance sampling ratio here, as we defined it previously, multiplied by the expected outcome for y. Okay, so this is exactly a proof that we can use the importance sampling ratio in order to find the expected value of some unknown behavior or some target behavior, not the one that we are using to sample trajectories for. So let's see how this would work in practice for our case, for the reinforcement learning, or for the Monte Carlo control algorithm. So in this example, let's assume that our behavioral policy is a uniform distribution between going left and right. Okay, so a 0.5 probability for going left and a 0.5 probability for going right at each state, at each non-terminal state. However, our target policy says go right with probability 0.99, almost always go right, but also go left with 0.01 probability. Okay, some very low probability. Now let's say that we sampled the following trajectory using our behavior policy, right? Policy B. So we started at W, went right, and observed and exited and observed a reward of +10. So now we would like to compute the Q values estimates not for our behavioral policy, not for B, but for our target policy, for pi. And we're going to use importance sampling. So we know, as before, currently we only have a single trajectory. In a second I'll introduce another trajectory. But we'll have to, for each state that we're going to compute the state value for, so currently we're doing it for W, we're going to compute the G, which is simply 10 because we assume a discount factor of 1. And we'll multiply that by importance sampling ratio at each time step. Okay? So the importance sampling ratio here for going from W, taking action right, is 0.99, probability of taking right under our target policy, divided by the probability of going right under our behavioral policy, so divided by 0.5. And same goes for taking right at state X, right? So here, going right here. So again, we have to multiply that by 0.99 over 0.5. So at the end, this results in 3.96 multiplied by 10. Now this is a bit of a weird result because it will tell us that we need to update the state value, our state value estimation for state W, to be 39.6, which seems a bit weird as our biggest the reward that we actually observed in this in this episode is plus 10. We inflated it 4 times, right? So this shows us that ordinary importance sampling, or the simple case, right? The simple importance sampling as we saw it so far, it is indeed unbiased, right? So I showed you that it is unbiased, but it has high variance. It has significant variance that we would like to address, right? We don't want some noisy estimation that will cause our policy to bounce around the state space. It might be not that bad in these small state spaces, but of course once we go into bigger and bigger problems, that might be an issue. We want to avoid noise as much as possible. Okay, so just to complete this example, let's say that we then sample a second trajectory, again using our behavioral policy B. So now from W we went left, we go to U, right? We have this trajectory going left and then exit, observe the plus 1. And again we need to update our state estimation, state value estimation for W. And now we take an average. Now we have two trajectories to average over. But again you can see that our importance sampling ratio provides us with some wild values. In this case, it will give us a probability, a weight of 0.02 for the second trajectory that we saw. Okay, so that actually won't provide a significant impact on our state estimation. Does that make sense, Babab?
It's a high variance, right?
No. Right, does that make sense that our second trajectory, our second sample trajectory, has such a low weight to it?
No, because as you saw previously,
right,
it seems to be overshooting. So now it's undershooting, I guess? I don't know, like large variance.
Well, right. But look at the second trajectory here.
Mm-hmm. In terms of the probability value?
Right, so no, indeed, no, that's fine. It gave us a very low weight, but actually...
It's close to the true weight.
This is okay because, you know, the probability that our target policy will actually follow that trajectory is indeed very low, right? That's fine. That should be fine. Okay, so let's see how can we deal with these high variance estimations. So a very simple trick would be to normalize our importance sampling ratios by the sum of important ratios. Okay, so each time, instead of simply multiplying by the importance sampling ratio, we'll multiply by the importance sampling ratio that is normalized by the sum of importance sampling ratios we observed so far. So 3.96 will be divided by 3.96. That's the only importance sampling we have. We only had this single trajectory. But this will result in actually a pretty good estimation of 10, right? Which is actually the accurate estimation here. By the way, it introduces some bias because, well, it's not the value that we previously proved to be unbiased. So it makes sense that it is biased. It does introduce bias, but it helps a lot with the variance. Okay, and for the second trajectory, we'll do the same computation, but we'll now divide it by 3.98, which is just a summation of our importance sampling ratio. Okay, ordinary importance sampling is unbiased, while the weighted version is biased initially, weighted importance sampling. However, ordinary importance sampling results in high variance, while weighted version has a bounded variance. We won't prove that, but it has some nice assurances regarding the variance. Okay, so let's see some results. How will these two approaches work? So here I'm showing you a curve for ordinary versus weighted importance sampling approaches when combined with a Monte Carlo control algorithm, as we saw previously. Here we're just trying to estimate a blackjack state, right? Now we have a target policy and a behavioral policy. So hopefully, I won't explain what blackjack is. Hopefully, the audience, you understand. If you don't know blackjack, it's a simple game. Maybe just pause the video now and take a quick look on Wikipedia or something, and then come back. But in any case, you know what? It's not that important. Even if you don't know what blackjack is, it's not really important. What's important is the curves here, and they are usually the same for any. Don't worry too much about that if you don't know what blackjack is. Anyway, the target policy for those of you who know how to play blackjack is hit on 19 or below and stay otherwise. So in blackjack you only have two actions in every round. Either you hit or stay. Okay. So our policy needs to define some distribution over these two actions, right? So our target policy is a deterministic policy, that's fine. As long as it's covered by our behavioral policy, and it is. Our behavioral policy is random uniform, so 0.5 probability of hitting or staying regardless of the state. Both Monte Carlo with ordinary importance sampling and Monte Carlo with weighted importance sampling converge to the true value. Okay, the true state value for the initial state. And here on the y-axis you can see the mean squared error. So how far off is our estimation from the true value. Of course we would like to be as low as possible to have a mean squared error of 0. And the x-axis is the number of episodes, the number of time we played blackjack. And of course we're doing reinforcement learning. Over time we want to get a better and better estimation, okay, of our state values. And you can see that indeed weighted importance sampling provides much lower error initially, while ordinary importance sampling, while being unbiased, has a very large variance, a very large error, initial error. Okay, so usually I would say as a rule of thumb, the take-home message is that you should implement weighted importance sampling. In most cases, it is significantly better or faster to converge. Although, of course, both approaches are correct. That is, both approaches do converge eventually to the true value. Okay, so just to see to allow us to go over the pseudocode for off-policy Monte Carlo control. For estimating, so this is not, we're not updating a policy, it's just for estimating some target policy pi. Sorry. So this is off-policy Monte Carlo controls. This is specifically for learning pi star. Okay, it's not only for estimating, we will use the estimates in order to converge on pi star. So I'm providing you the pseudocode here. Initially it looks similar to the on-policy Monte Carlo control algorithm that we've seen previously. So here we set our behavioral policy as any soft policy. We generate an episode using B. Then we update our returns, the G values, the capital G values, right? By accumulating the reward after some time step T. We set W, our weight, to be 1. Initially it will be 1. But over time it will be 1 over the joint probability for observed actions from following B after time step T. This eventually is equal to the importance sampling ratio because the target policy is deterministic in our case. Okay, so if the target policy is deterministic, I can always set it as 1. And if we diverge from the target policy, we will just cut or break from our loop, because all of the probabilities prior to that will just be zeroed out. Now we go back in time, so we start from our last time step T at the end of the episode, and we go back in time until we get to a state or we get to an action that doesn't follow our target policy. From that point on, our importance sample ratio will just be 0. So we can just break at that point. So now what we do, we accumulate the returns and we discount future rewards and add immediate rewards, right? So RT plus 1 is the immediate reward. And all of the previous rewards are discounted by gamma. Of course, over several time steps, the older rewards will be discounted more and more often. We'll have gamma to the power of how far they are into the future. We compute the cumulative sum of importance sampling weights affiliated with any ST-AT pair. This is what we need to accumulate for weighted importance sampling, right? We're gonna use this as the normalizing factor. We're using the weighted version of importance sampling. We do incremental update of Q values. So this is a weighted moving average, as we've seen before. Okay, in order to provide more stable learning. This is similar to temporal difference learning. I think, did we discuss that before?
We discussed it for stateless.
It's for state. Okay. So in any case, we'll later also revisit temporal difference learning, TD learning, over and over again. For now, I'm sure that we already covered the moving average, moving weighted average. So this is just a moving weighted average. Then we update our target policy. So as I said before, the control algorithm, the off-policy MC control, also try to converge on pi star. So we always update our target policy based on the best Q values that, to follow the best Q values that we know so far, or the actions that results in the best Q values, right? The argmax action. At any time step, when you go back in time, if we diverge from our currently known best policy, our target policy, then we say the importance sampling from this point backward will just be 0, so we can break from out of the loop, right? Exit the for loop, and we'll just sample our next trajectory. And then also, eventually, we update the joint probability by multiplying by the importance sampling ratio at time step t. You have to please notice that as I said previously, the target policy for any state in our moving back in time, any state that we observe, is 1. It has a probability of 1, because else we would have broken out of the loop a step before, right? This is why the nominator is always 1 here. We assume a deterministic target policy. Okay, so let's see a running example just to be able to see that we understand how this algorithm would work in practice. And again, for the running example, I'll ask Vabhav to present the process.
Hey, hi everyone. So like we saw before, very similarly, we have randomly initialized Q values. This time we have a list C, which we will use to, I think, keep a...
this is for the weighted.
The importance sampling weights, right? So I think...
No,
sorry.
The weighted version, right? So when the normalizing factor.
Yeah, so this would be the sum of the importance samples. Would that be it?
Right,
yes.
Yeah.
So C would be the sum of the importance sampling ratios that we've seen so far in the episodes that we've sampled. And pi is our randomly initialized soft policy.
Pi, no, in this case, for the control, we are trying to converge on pi star. So pi s is actually a hard policy. You see, it's just a function of s.
So in our case,
always return. So in this case, it's the target policy. It's fine. We just need our behavioral policy to be soft to provide coverage.
Okay, so this is our target policy.
Yes.
All right.
We would like that to converge on pi star eventually.
Okay. So yes, and this is our behavioral policy, which we'll be sampling from, which is a uniform policy giving equal probability to going left or right in each state.
Right, but it doesn't have to be. So this is just an arbitrary soft policy.
It could be any behavioral policy. It could be any set of probabilities here. I think the only condition needs to be that it has to have a non-zero probability if that state and action pair has a non-zero probability for a target policy.
Right.
Yeah.
You have to have coverage.
Exactly. So if for X here in a target policy taking action left has a non-zero probability, we will have to have the same non-zero probability. I mean, not the same probability, but non-zero probability for our behavior policy. If this was 0, we could not use importance sampling. So we have any soft policy B, and we use it to generate an episode, which is represented by this trajectory from X. Let's see. From X we go X we go to state W and then exit. So upon doing that, so we do this like Dr. Sharon said. Now we took a trajectory. We went from X to W and exited, and we start calculating our values G from the back of this trajectory. So starting from the last time step, which is at state W, we took action exit and we saw -100. So our immediate reward there would be -100, and our future discount reward would just be 0. So I think if we see the updated values, that's not. So yes, so we don't have a list here for G, but yeah, G right now would just be -100 for because it was 0 before. So yeah, it just alpha into 0 plus the immediate reward -100, and then we see W. We are keeping it as 1.
W was initialized to 1, and we are now looking at the final time step before we went out of the episode. Exactly. That was time step 1. We started with 0. And we had time step 1, and then we exited. So we're going back in time. We start at t equals 1.
Yes.
Okay. The G, the return is -100 at this time step. C is updated to be the current C value. So if you can go to ST80, so W and exit.
W. Yeah. So for here
0.
For state S, if you take action exit. We got -100, and then for state X we took action left.
No. So we're doing it one at a time. Currently we're at the final state was W. So let's do the update for W. G is -100.
Yes.
W is 1. It's just the initialized value. Now we update C. Right.
C is, like I said, running sum of importance sampling.
Right. So that's it. You can see there. It's a table there on the left.
Yes.
So C.
So C was initially 0. Yes. C was initially 0. We just add W to it, which is 1.
Yes. And C is again for a state and action. So for W exit, it's 1.
Yes.
Okay.
And then for the same state and action pair, we use G and C to calculate the updated Q value. Here, the Q value was initially 0, and W and C over here are 1. So this would just be -100, like here. -100.
Right. So it's -100 times the
times W by C, which is just 1.
Right, which is 1, because why? Because that's the only action that you can perform in W. You can only perform exit. So both policies, both the behavior and the target policy, will do that with a probability of 1. Right. So the the weighted importance sampling ratio is just 1.
Because both have to take the same action.
Right.
Yes.
They don't differ.
There is only one
action. They don't differ from
yes.
Right.
Then we use these updated Q values to find our new policy, which would see which is the new best action to take in each state. So right now in state W, there's only one action. So
no, we don't update. IST.
Yeah, so this should be for state W. There's only one action anyway, so that'll remain unchanged.
You're right.
And then so we missed a condition here. So if AT is not equal to this state, so here our action was to go take exit, and our new policy's action is also to exit. So since they are the same, we would not exit the for loop.
Right, we just update our importance sampling ratio. Right?
Yes. But why is that? Now, if we do see the same action, why do we exit the for loop? Is it because
If
the
we
policy...
don't see the same action.
Okay.
Right? If we see...
Sorry, yes. If you don't see the same action...
Then we exit. If we... Because then it will zero out the importance sampling. Why? Because the target policy is a deterministic one. If it's not the same action, then the importance sampling ratio, accumulated importance sampling ratio, W, will just zero out.
Okay.
Okay?
Alright.
It will be 0, and from that point onwards it will be 0. Right?
Okay.
Here. But if it is the same, then we can set the denominator to be 1.
Mm-hmm.
The probability of 1 that we took that action with our target policy.
So if this was not a deterministic target policy, we
Then
would not have that condition.
Right. Then we'll use something slightly different. But I'm specifically would like to show the version that converges on pi star, right? The control problem that eventually converges on pi star, which is a deterministic policy. We assume that it is a deterministic policy in this case.
Okay, thank you. Now we update W. W was previously 1 into 1 by the probability of taking this action in the state, which is also 1 because there's only one action you can take in state W. So W will now become, wait, it says 2? Or would it be 2?
Where?
On top.
Because you update W to be W multiplied by 1 over the probability of taking the...
Oh, sorry, that's half, right? Yes.
Right, it was
yes,
half.
Yes, that's half. Sorry, I thought the probability is 1. So 1 by half here. 1 by half will be 2. So W will now become 2.
Right.
Yeah. And then since we didn't leave the for loop, we repeat. We now move from state W backwards. So we started in state X. So from W now we're looping backwards. Just calculate state X and action left.
Right, this time step 0.
Yes.
Was back in time.
Yes. So now we're going back in time to the first state and the action taken at that point, which was left.
Right. So we update our return by multiplying the previous return by the discount factor and adding the immediate reward, which is just 0.
Yes. So if we update the returns, we get minus 90 for state X action left, and then C would just be 1 plus W. Oh, sorry. Yeah, we did set it to 1 before, right? So now it'll become 3.
No, it was 0. The C you can see here. This is the table of the C values, right? So
yes.
It was 0 before, for being at state X and going left, and now it becomes 2.
Sorry. We made it 1 here. So 0. This one was still 0, and now we added W, which is 2. So now it's 2. And then the Q values updated using these, which we get as minus 90. Before it was 4. Now the actions value.
Right. It's exactly the G, the return that we have so far, because we use weighted importance sampling.
Yeah.
Right. So it's only a single trajectory. So it doesn't change. The whatever importance sampling ratio we have, it will be weighted by itself.
Okay.
Right?
So we're not dividing by the number of episodes.
The number of episodes is 1,
okay.
Right?
Always
so this always happens in the first episode.
Yes.
That you update it to be exactly the returns.
Okay.
Okay. In the next round it will change.
And then we update the policy. We see that now it might be better to go right in state X. The new state is not the same. The new best action for state X is not the same as the action we took. So I guess this should
at this point
be conditioned to exit. So now we exit the for loop and we come to the outer loop. So this loop was us going down the trajectory and updating the Q values. And this auto loop is to actually generate the episode from which we generate, we can update our Q values and these episodes. So for each new episode, we would reinitialize G and W because we want our important
G
sampling.
is simply the returns for the episode. So yes, each episode has its own return. And W is the importance sampling ratio. We start at 1.
Yes.
So saying, listen, once you exited, it's exactly the same for both our target and behavior. And as we go backward in time, our importance sampling ratio will start reducing over time. Right?
Okay.
The probabilities will start diminishing because our two policies will start diverging from each other.
Okay.
If they are different.
So we initially set it to 1 because we don't know how different they are, and then as we loop through this,
No, we initially set them to 1 because after exiting, they behave exactly the same.
Okay.
Nothing happens.
Okay, they are the same.
Right.
Okay.
But as you go, as you start going back in time, well, they differ from that point onwards,
Okay.
right?
Yes. So at the last state, they'd be the same because it's the terminal state.
Once they exited, they exited.
It exited. Yeah, makes sense.
Okay. Yeah.
Okay, so then we go through. So now we exited from the previous episode and we're starting a new episode. So we generated a new episode. We reinitialized our G and W values, and we calculate the returns for this new episode. Now a new episode here is going from X to Y to X, Y, and then exiting at Z.
Right.
So it's going completely to the left.
Right.
Right. In this case.
So now again, you start your loop. You're starting at this time step 2. That's your last time step, and moving forward in time.
Yes.
Okay. So hopefully.
So let's go through the.
Sure.
Yeah.
Let's go quickly.
We have the returns 10. We similar to before, we see that C will remain 0. For this, Y is C 0.
No. So again, this is the last step.
The last
state Z.
Yes.
Right.
So we're looking at state Z,
So it's
action,
now 1.
exit. We get a 1 for C after we update it, and we see for Q, we update the Q values, but the policy will remain the same in this case because there's only exit action. So we can just go to the T minus 2 state, which would be Y, and taking action again, going east, and we see that because of the discount ratio, G will now be 9. Your C was 0, so now it becomes 2 as W is updated to 2. Q value is updated to from 1 to 9. So this was a good action, and our policy. Upon updating our policy, we see that the actions kind of remain the same. It's still optimal to go to the right. So we have the policy remains the same. We don't break out of the loop, and we update W. It was 2. Now we into 1 by 0.5, so it's 4. And okay, and then we loop through it again, and I think we see the same actions. Sorry. We'll
Go back in time to time step 0.
to time step 0.
Do the same
thing.
Same type of
And
updates.
now we've actually completed the loop. It's not like we've broken out of it. Now we just completed the loop. We've finished all the states and we've come out of it. And
we sample a new trajectory.
we sample a new soft policy, generate,
and that's,
and generate a new trajectory, and so on and so forth.
Yeah, okay. So thank you.
But normally, I guess we would have a convergence condition or something to stop, right?
We repeat this forever, for now.
Okay.
Okay. Yeah, you can add a convergence condition, but we are dealing with online optimization problems, so we can assume that we continue this process forever. That's fine. And of course, right, if you observe that performance convergence, that you can also stop and return the policy. Okay, so thank you for the running example. Hopefully, everyone could follow. In any case, I do suggest taking a minute, going back and solving everything yourself and seeing that you get exactly the same values and that you understand how this works. If something is not clear, please send us an email. Either me or the TA.